Okay, in this video I'd like to talk about energy and specific heat. And energy and specific heat seem to be something that almost seem mystical to a lot of students, and I kind of struggled with it a little bit whenever I first learned it, if I remember correctly also. But hopefully this video will kind of demystify it and make it a little bit simpler for you. So let's talk about just energy at first, right? When we think of energy, we think of maybe the food we eat, and the food we eat has calories, and you burn those calories to create heat and use that for energy and so on and so forth, right? Well, the measurement for energy is generally in joules. Joule like that, just abbreviated J, capital J. And we can add prefixes to this like, kilojoules or megajoules, and things like that to increase, or decrease the value for it. But this is our base unit, would be joules right there. So if you see something that's like, I don't know, 800 joules, that's referring to a specific amount of energy for something, right? Well, if we plug in a ratio to that, like let's say for every 1 joule, right? Or I'm sorry, let's say for every 1 calorie, I'll just abbreviate calorie like that, we have 4.184 joules. Well, now we can kind of swing this in a little bit of a different direction. If I say I have 8,500 joules, I can tell you at that point how many calories are in that. Because I know for every 1 calorie I have 4.184 joules. You just grab your calculator. 8,500 times 1 divided by 4.184 equals 2,031. We've got 2 significant figures, so really just 2,000, or 2 point, if we were going to put it in scientific notation, we'd have 2.0 times, what is that, 10 to the 3 would give me, 2,000, a 2 with 3 zeros behind it. So that would give us 2 significant figures for our 8 and our 5 over here. So that's calories. Now the funny thing, and especially ladies are always shocked whenever they hear this, but whenever you see calories on the side of your nutrition label, it's often in kilocalories, and they just call it calories. I think like a capital C maybe is kilocalories, and a lowercase c is regular calories. I don't quite remember that off the top of my head, but almost all of your nutrition labels are going to be in kilocalories. So you may think, oh, this is just 1 calorie, when in reality it's 1,000 calories. And that has largely to do with that 1 joule of energy is really not that much energy. And 1 calorie is really not all that much energy either, consequently. But let's talk. Let's switch it up a little bit here, right? We've talked about if I have 800 joules of energy, how many calories that converts to, so on and so forth. That's a little bit more easy because it's just kind of plug and chug. You have your ratio. You can use dimensional analysis and solve for it. What if I have something like, say, water that has a specific heat and it's liquid and solid state? So let's say I've got water here, right? H2O. And at its liquid state, at water's liquid state, its specific heat is 4.1. I think it's the same. You'll usually get this from a chart, and I'm just getting it from a chart right now because I don't have it memorized. But yeah, 4.184. And specific heat is always going to be joules. Well, I shouldn't say always. It's always going to be joules or kilojoules or megajoules or something like that over grams or kilograms or megagrams or something like that times degrees Celsius, but you may see this in degrees Kelvin or in Fahrenheit. It's always going to be your unit of energy over your unit of mass times your unit of temperature. So it could be any one of those. It's not necessarily, married to joules or grams or Celsius. It could be kilojoules or kilograms or Fahrenheit or Kelvin. But anyway, that's what the specific heat is. So we know we have a specific heat of water at that. So how are we going to solve for how many joules of energy, like what we were talking about up here, are in that water? Well, we need to take some other things into consideration. We need to take its mass into consideration. How much water are we talking about here, right? We need to take its volume into consideration. How much space is it occupying? What's it weigh? How much space is it occupying? Right? Well, there's a formula that someone's came up with, and I don't remember who off the top of my head, but he was someone much smarter than me, and he came up with this formula that energy, or Q, equals the specific heat times the mass times the, I said volume, I really meant to say change in temperature. Change in temperature. Because if we're putting energy into some type of a system, into an equation, maybe our system is a cup of water. If we're putting energy into it, it's going to have a change in temperature. Well, that's represented by the symbol called delta and a T for temperature. Delta just means change or difference, and T stands for temperature. Now, the delta T, or the change in temperature, is always going to be your final temperature, or T final, minus your T initial, or your initial starting temperature. In word problems, they'll word this like, we started at 15 degrees temperature and it rose to 20 degrees temperature. So you would have 20 minus 15 would be a 5-degree change in temperature. All right, so we need to know the mass and the change in temperature. All right, well, let's say I've got liquid water, and I know that liquid water's specific heat is 4.184 joules per grams degrees Celsius, and I have 550 grams of it, right? So let's say I've got, let me change this degree, I've got 550 grams of water, and let's say I had a rise in temperature. I put in X amount of heat into this system, into this beaker of water, that's 550 grams, and the temperature rose from 60 degrees to 70 degrees, right? How much heat did I put into that beaker, into this little beaker of water right here? How much energy did I put in that to make it rise from 60 to 70 degrees Celsius? Maybe specific here, Celsius. All right, so we're going to use this formula, and we're just going to plug and chug at this point, right? So I know the specific heat is 4.184. Let me scroll down just a little bit. 4.184 joules, that's an 8, for joules per grams times degrees Celsius, times my mass, which is 550 grams, times my change in temperature. This was my final right here. This was my initial. So that's a 10 degrees in temperature change. 70 minus 60 is 10 degrees Celsius. All right, all this is going to equal my energy that I put in to do that. So you just grab your calculator here. Grab mine. We've got 4.184 times 550 times 10. So that's 23,012 joules. 23,012 joules. Sounds like a lot, right? That's a huge number. Well, we only raised it 10 degrees Celsius. So, I mean, when you think about it, 10 degrees Celsius really isn't that much of a difference. Whenever you pull something out of the, soda out of the refrigerator or whatever, it changes more in temperature than that if you leave it sitting there long enough. So, that's really not a whole lot of energy. So kind of like what I was saying with the calories, 1 joule really isn't worth that much. We could really even say, that this is 23 kilojoules, right? And give it a more round and even number. If we were going to take significant figures into account with this, we would not do the 10 degrees Celsius. We wouldn't figure that in. For significant figures, it would be the 5s here. For 2 significant figures, this would be 4. But we wouldn't say this is 1 significant figure and say, oh, well, I've got 20, round down to 20. It would be 2 significant figures there. But anyway, that is a standard heat and energy problem. I'm going to do, in the next couple of videos, I'm going to do more problems that involve this specific heat and this formula right here, because it can get a little bit tricky as we go. Anyway, hope that helps. Thanks for watching.